And yeah, I'll give you 5-minute warning.
Thank you. Yes. Well, thank you for being here, and let me thank Alec as well for setting the stage. That was a pretty good pitch. I'm going to be talking about data, but not necessarily data that, like, everyone is working on, but data that are prepared, that are curated for machine learning applications, that are fair, F-A-I-R, findable, accessible, interoperable, and reproducible, and can be used by machine learning applications. This is what we call benchmark datasets. So, all right, it takes some time. Anyway, I'll start with a simple definition. You can find many around, but that's the simplest one I could find that I agree with. Then I'll try to connect this with how you do forecasting tasks by relying on this data, which is kind of a traditional notion, that of the theory, and I will explain what I mean. Then I'll talk about verification briefly, some examples, expansion of benchmark datasets, and a property of benchmark datasets, which is similar to the property of potential fields for those who have a solar physics background. Any superposition of a potential fields is a potential field itself. Any superposition of benchmark datasets is a benchmark dataset. And finally, my conclusions. So, benchmark datasets, they are an integral part of data mining and machine learning, where new techniques or algorithms are tested against some arguably high quality. And by high quality, I wanted to make this clarification here. I do not necessarily mean high quality data, because if you want to go into operations, you have to rely on near real-time data, which are imperfect. But if you're using a benchmark data set, it has to be well curated. Imperfect, yes, well curated as well. So that's what I mean high quality. Data sets to demonstrate the reproducibility, effectiveness, and efficiency. We are relatively new to this kind of business, but if you look around in the general literature, there are several frameworks, infrastructures, resources of benchmark datasets. One of them is Kaggle. The other one is ImageNet, in which you can find different image datasets that are well curated, and they are used for competitions. Competitions is the name of the game over here. Comparing between different machine learning methods is a competition between different machine learning methods. We are not looking for a winner so that to cheer the winner. We are looking for something that works. Okay? So, all in all, you have the classical notion of a hardware, some servers, disks, etc. You have the platform on which the tools are based, data handling, machine learning, and visualization. Benchmark datasets come over to clarify or to refine this picture by saying, I have all previews, but I'm going to need some domain expertise and experience in transforming a dataset into tangible knowledge, right? Taking a benchmark dataset, using some domain expertise, and making something tangible, a result that I can rely on in future steps. So, let's say you have your data, you need your data. How do you approach a forecasting task, any forecasting task? And for brevity, I'm only focusing on forecasting tasks. FLARE, CMEs, SCPs, the CME arrival problem, whatever, you name it. What I would argue for is that we apply the classical notion of a theory. What is a theory? A theory is a set of concepts, empirical notions that are coming out by observations and stuff like that, that have this property of creating testable predictions, right? So you test a theory. If it survives, then it survives to live, for the next day, and you test it again and again. If it doesn't survive, you have to either drop it, dump it, or refine it so that it survives. So you have this kind of thing. You have your data. Of course, you're going to need to test your theory. You have your forecast model, whatever it is. This could be either conventional statistical one, or machine learning, and you have verification. Verification is all-encompassing. It does not only apply to the performance. It applies both to model and to data. So the whole thing is all-encompassing over here, because this is how you progress if you want to really make a tangible progress that I mentioned before. So verification. You have data verification, you have model verification, and you have performance verification. In terms of data, you verify your data by making sure that you have a benchmark data set. You have taken out the ambiguities, you have taken out the outliers, you have made it homogeneous by filling the gaps, interpolating the gaps, checking your sources, put the right flags so that you know what you're talking about, and desirably partitioning. I will explain what I mean by that. The model verification, I'm not going to say much, but it's pretty much boils down to making sure that your model works as expected. There is a very nice technical report by Thacker et al. Back in 2004 in which you can get some pretty good information about how you do model verification. And then you have performance verification, which is a talk in itself. I'm not going to refer to it very much, but I'm going to say that this depends on whether you have a binary or a categorical forecasting. Yes, no in terms of two samples or several categories, whether you have a probabilistic forecasting, and then you have different skill scores and metrics. We can talk about them. But the overarching idea is that of a skill score. You have any parameter that you can calculate by your model. This is a score over here, the S. You have a reference model, you have a perfect model, and you have, again, your reference. By creating this ratio, you have a skill score. You can call it Breyer skill score in probabilistic forecasting. You can call it, Appleman skill score or Heidke skill score in binary forecasting. That's the overarching notion here. So verification. Here are some examples. Michele Piana mentioned yesterday about the FlareCast project. They are available online via API. You can get this data about flares. The positive sample is about 5,000, more than 5,000 C-class, 500 M-class, and 35 X-class flares over solar cycle 24. And you can see over here the general attributes. You can retrieve this data from the web, and you can determine, you can define your training and testing samples out of those. Quite a bit of work has been done by the data mining lab at Georgia State University, and this is also accessible at the Harvard Dataverse, in which case they have taken the entire cycle 24 and they have partitioned it. Remember, I mentioned partition. Partitioning is not homogeneous, as you can see over here, but it relies on certain properties. Here you get the imbalance ratio, which is not similar between the partitions, but they have similar absolute numbers of the positive and negative sample. And if you have partitioning in there, you can say, okay, I'm going to try to train on partition 1, test on partition 5, and validate on partition 2, and vice versa. So you generate different combinations of things to do there. In terms of SCP events that Alec was talking about, there are at least two I can think of. One that has to do with the PhD work of Shuman Throtti at Georgia State. It's also available at Harvard Dataverse. You get only 245 eligible SCP events over 3 solar cycles. So you can imagine how rare this phenomenon is. And then you have Athanasios gave a talk yesterday. He has his own data set, which is also available. You get about 314 eligible SCP events in his database out of tens of thousands of flares and CMEs. So all these are available, and you can get those if you want to. And then very recently, something that I consider quite interesting and important is a magnetic polarity inversion line dataset that was put together by Anli G at Data Mining Lab of Georgia State. The same way we create the sharp metadata from HMI magnetograms, you focus on the polarity inversion line of active regions right here, and you create a set of metadata that you can also find available in Harvard Dataverse. And why polarity inversion lines? If you are a solar physicist who deals with eruptive phenomena in active regions, then you know that polarity inversion lines is arguably the single most important feature in active region. The strength, if you quantify its strength, then you have a good chance of getting an idea about eruptions.
You have 5 minutes.
Thank you. Whether you forecast or not is a different story, but in this case, you cannot go about forecasting without understanding first. So we need to understand. And this is why such a data set, a benchmark data set, is quite useful. So we are talking about more than 4,000 HARP time series from HMI over cycle 24, in which you can get the metadata and work with. So if you have a benchmark data set, you have a list of instances, you have a properties, a vector of properties for each instance over here. What you can do about it? You can horizontally expand it by doing what? Either increasing the number of instances in the same format, or increasing the number of predictors, so n prime, which is bigger than n over here, so that you improve your statistics. That's a horizontal expansion of a benchmark data set. If the data are being collected the same way, then the horizontally expanded data set is also a benchmark data set. Then in terms of the vertical expansion, because you have that as well, you might keep the same number of instances and the same number of predictors in each vector, but you add some columns right here, and you associate these events with some other events. And I'll give you an example. This is a list of flares, just an abridged list because this table is pretty big. But just keeping this list of flares over here, if I associate them with CME information, how many of these flares were associated with CMEs, and again, all these flares are associated with CMEs, and then with SCP event information right here, then I have started from an initial flare data set, and I have expanded it vertically to take into more problems, eruptive flares, and SCP events out of those. So better statistics by horizontal expansion, more problems by vertical expansions. And this kind of thing makes sense because it is physically consistent, self-consistent, and it can make sense if you try to have a holistic view of interconnected, intertwined problems. Right. So in essence, if you have a benchmark data set, you can fuse different things together like different bunches of Lego blocks. If each one of those is a benchmark data set created pretty much the same way, then the entire conglomeration of data sets is a new benchmark data set. And this is how you improve your statistics. This is how you get into new problems. This is how you make better sense physically, because above all, we are physicists, okay? So that's my last slide here. I argue and I propose that generic theory treatment is a paradigm if you want to take into solar weather forecasting tasks. In this case, you definitely need benchmark datasets that are homogeneous and well curated to allow machine learning applications to go and exploit them, to try to compare between different models. It is meaningless to compare between the scores, the skill scores or the statistics or metrics in general between different models if you're not using the exact same data sets. Even if you're using benchmark data sets that are different from run to run, then you cannot make sense in comparing. You have to use the exact same thing. That's why it's important to have these sets available online, and this is what other communities have done with Kaggle and ImageNet, and we are just starting appreciating the whole thing here. So they are expandable benchmark data sets. You can improve your statistics. You can take on new problems. And also, like potential fields, the superposition of different benchmark data set is also a benchmark data set. And this makes sense both in physics and in statistics. And that's all I have. Thank you.
That was brilliant. Thank you. Have we any questions here in person? Yeah, Rosita?
Yeah, we can have a follow-up discussion, but what makes a catalog a benchmark database?
What I mentioned before.
Human-made catalog, not automatic.
So it needs to be homogeneous. It needs to adhere to the main principles, which is findable, accessible, interoperable, and reproducible. It needs to be homogeneous. It needs to have as fewer outliers as possible. You need to cross-check the sources because you take different sources. You might have NOAA, you might have NASA, you might have different things. You make sure that these sources are correct. You do everything to make sure that different parts of the catalog are self-similar to each other and to the rest of the catalog. That's a benchmark dataset.
And where should we post it? Some of our catalogs are freely available, but it seems they didn't get much attention from the community, even less from the machine learning. So we have to go around and advertise
Yeah, so I would think that, and I would propose that the best course of action here is to have a paper about a benchmark dataset so that it becomes visible to the community, and then to provide the dataset itself into some repository that has DOIs, that has document object identification, because in this case you can keep a version control, you can have a data set over there that can be version 1, version 2, and everything. And it is easily not only interoperable, but also it can be cited pretty easily. So if I just give the DOI and I say, okay, we're going to test such and so machine learning or deep learning methods on this data set, that's a DOI, then it can be done easier.
We have a question online from Veronique.
Yes, hello, and now I'm with my camera. Thank you, Manolis. You talk about interoperability. This means, as I understand it, to have metadata for this data set, and that these metadata are somehow standardized. So for interoperability, you want to have different software that are able to use these data set, and for that, they need to talk a common language. So that is to know metadata that are common. So by metadata, I mean things as simple as if you have, say, a catalog of flare, the name of an active region, or the name of the magnetic flux, you can have different catalog of active region, and the area is mentioned differently, active region type is mentioned differently, so the name of the columns of the catalog. So do you have any comment on that, on how, we could progress towards a more standardized way of describing this metadata?
Yes, thank you, Veronique. And this is an important discussion indeed. We need to talk a common language. But let me make this clarification because I didn't do that earlier. By a benchmark data set, I mean both data and metadata. So a benchmark data set can be a set of images, magnetograms or EUV images that have been produced and have been processed the same way, or metadata thereof. So the examples that I gave are mostly metadata in the sense that they are sharp metadata and additional metadata that have been generated in a consistent way. That's one thing that I wanted to make clear. And then the other thing is that if you're combining different benchmark data sets, then you have to decide that the labels are going to have the exact same names, because otherwise you end up with something which is not consistent. But a benchmark data set assumes by definition that there is consistency. So if I'm bringing different data sets together, then I have to make sure that the column names, let's say, and the row names are going to be exactly the same, to put them together.
But to put these names, this is somehow a common community effort to
Sure.
decide on these labels or to have a mapping.
Sure.
To allow for a mapping.
So let's say I have two data sets that are published somewhere, okay, and then the two groups that created the data sets decide that they would like to merge them, okay? In this case, they should be coming together and they should be agreeing on how to homogenize the terminology between the two data sets into a single terminology that can take both of them and present them as a new benchmark.
Okay.
That's
Okay,
great. I
thank you.
think, yeah, just in the interest of keeping us going, we might leave it there. But thanks again, Manolis.